Hello, this is the first installment on linear systems. And by linear systems, I will mean systems of linear equations. The easiest such will be just one equation with one unknown. And being linear, it will look like that. But even this simplest one shows all the ramifications one could have solving linear systems. And yeah, they're kind of straightforward and we don't talk about them, but they really show very well what happens in general. So if A is non-zero, we can we will have a unique solution. Namely, X will be the ratio of B and A. If A is zero, we might have two outcomes depending on what B is. So if B is zero when A is non-zero, we'll have an equation which is when A is zero as well. 0 times X equals 0, which is just a vacuous equation, and it has infinitely many solutions, all values of X. But when B is non-zero and A is 0, we will have an incompatible, unsolvable equation, something which is 0 on the left being equal to something non-zero on the right, so there will be no solutions. And that is all about systems of just one equation with one unknown. But again, this example shows all the possible outcomes of solving linear systems of linear equations. We could have infinitely many solutions, we could have a unique solution, we could have a situation where we have no solutions at all. So these all three possibilities have to be expected. Let's look at a generic system of two equations with two unknowns as a next example. My unknowns will be x and y, and the coefficients will be from a to f. And as before, we could solve it, but now, yeah, we have to do intermediate steps rather than just dividing and writing the answer. So we could use just the logic and use the first equation, if it's non-trivial, if it's not just 0 equals 0, as some information about one of the variables, namely that variable which appears with non-zero coefficient there. So we could assume that the first coefficient A is non-zero. And then we can divide by this coefficient our equation and have an expression for x, effectively. So that's what happens when we divide by A. The second is unchanged. This transformation doesn't really change solutions of our system because A is non-zero. And then we could use the first equation as the answer for x in terms of y and substitute this answer in the second equation. So if we do that, I will keep the first equation unchanged. And in the second equation, I will replace x by its expression in terms of y, which comes from this, which will be c over a without b over a y. And then we have an extra copy of y with its coefficient, original coefficient, and then the right-hand side. So then we can just rewrite the second equation as just an equation of y, and we will be in the previous case of just one equation on one unknown, which is easy to solve. So doing some algebra which only affects the second equation, we will have y singled out. So how many copies of y we have? Well, originally we have e times y, and then we have this with negative sign, and d is a prefactor for that. So the total effect will be negative bd over a added to y, sorry, added to e. And then this product will be just a coefficient, just a number, and we can put it on the right-hand side where it belongs. And in doing so, we'll have to negate it, so it will be c over d, c times d rather, over a. So that is where we can now find y. We're still not doing anything with the first equation, just changing only the second. So y now, assuming that this coefficient is non-zero, otherwise we will have either trivial case, yeah, that will be this case, and there will be either infinitely many solutions or no solutions at all. So I'll be just looking for the generic case where I will have unique solution. So then I will be able to divide by e minus bd over a, and that can be simplified to just making clearing sorry, cd over a as well. So making common denominator in the numerator and in the denominator of this big fraction, and then get rid of it. So I'll have ae without bd in the new denominator, and then I'll have af without cd. And now I can substitute that into my first equation and have the answer for x effectively, because x will be equal to c over a minus b over a times whatever y is, and that's what y is. And if we do the math, then we'll have the same denominator, but the numerator will be bf without, what it will be, ed or de. Sorry, CE. No, be careful. Let's look what happens. So A will be appearing as an extra factor in the new denominator, but then if after cancellation of the numerator, it will have to cancel out. So there will be fd, that's what we'll be left with, or df. Oh no, doesn't look like will be both with f, so let me do it again. So there will be a term which is the product of c with this factor, which will be ace, bcd, and then we will have BCD appearing again with a different sign in here, so BCD will cancel out, but ACE will survive, and then A will cancel out, so CE will be this factor. So that's it. That answer, which is a generic case, which is when the denominator is non-zero, which is AE not equal to BD, is called the Cramer's rule. So that is a generic, again, a rule which in this assumption that the denominator is non-zero gives us a solution, well, actually unique solution for the system of two equations. Now I'm going to do it one more time, but in a different way of writing it. So what I was writing is just the actual system, and then I was transforming it using the common sense. The method of solving linear systems, which is more economical, which is quicker to work through, is to first replace the system with what is called its extended matrix. So we just retain only important information. X and Y, our unknowns, are not going to change at all during the process. There still be X and Y at the end. We just need to find what they are. What is important are the coefficients of the matrix, and then the left-hand side will form the bulk of this matrix, and the right-hand side terms will be in this extended part. And then whatever we were doing, we can do with this extended matrix. So the first transformation we were doing is we were dividing the first equation by A. And that is a transformation which we can do just with these coefficients of the first equation. So the code, which I will be recording the transformations which I will be doing, and the code for this division by A in the first row will be this. And after that division, A will turn into 1, B will be divided by A, and so will be the right-hand side. The second equation is not changed in the process. So that is the first, what is called elementary transformation on the system. As before, these transformations we were doing, they were not changing the solution set. Well, we were assuming something like non-zero for the denominator, but under those assumptions, the sets of solutions for each of the successive equations, system of equations, was the same. That is, again, the same for these elementary transformations on matrices. They just encode the transformations of equations we were doing. So the second one is to substitute x in the second equation, so the second transformation. And I can do it just on the level of matrices in the form of row subtraction. So the transformation, please check that is exactly what was happening here. But on the level of matrices, I will be taking the first row of my matrix, multiplying it with a number so that the first terms will match, and subtracting. And as a result, I will get 0 here in the new second row. So that will be the code for the row subtraction. The first row which I'm subtracting is unchanged, but I'm changing the second, which I'm subtracting my first from. And I will have 0, and that was really the design of the transformation. I'll have 0 in the first component of the row as a first coefficient, and then the second coefficient will be whatever was there minus BD over A. And then on the right-hand side, I will have the same effect. So I will be subtracting the number, this number multiplied by D from whatever was there before, CD over A. So that is just, again, the code for this equation we have. And proceeding with transforming the matrix, now I can scale the second row by this number down and make the coefficient here 1. So that will be dividing by AE minus BD times A, my row 2. The first is not changed, the second becomes what it is, and then I will write the right-hand side as it is. after doing some algebra, of course. And then the first is not changed. So the final substitution of y in the first equation to find x now can be done again with the help of row transformations by just taking the second row, multiplying by the b over a, and then subtracting so that we'll have 0 here. And the code will be row 1 without b over a row 2. So the result will be just ones and zeros. Oops, this is a straight line. And that is really the code for the equations x equals something and then y equals something. And those something we computed before, this Cramer's rule answers are here. So that is a different way of writing the system, the transformations of the system, but it is more economical. It might not look much more economical for this simple example with 2 equations and 2 unknowns, but it is economical. We're not writing x's, we're not writing y's, we're not writing equation signs. Well, we're writing the bar instead of equation signs, but yeah, we are saving time by not writing the unknowns and not writing the summation symbols. And doing the transformations, these elementary transformations with rows is sort of more structured, and it is easier to see where we should do the next one and how we should sequence them so that we will get to the easiest form of our equation and hence the way of seeing the answer. So we will talk more in the next lecture about the general Gauss algorithm of how to transform a matrix of a system to its most easy to use form.